So I owe you all an apology. I decided to try something different and shake you a little bit out of your comfort zone that caused you to make some mistakes repeatedly. And I chose to do that by frightening you. Unfortunately, I overstepped and I knocked you back a little too far as your understanding of how math works. So I want to help build you back up. All right. So we're going to do just a review on sort of the relationships inherent in addition and subtraction, multiplication and division, and then exponents, so that you can rebuild your fundamental understanding and never distribute exponents across addition. I still want you to not do that. That's not a thing, and I'll show you why. So 10 plus 10 plus 10, repeated addition, is 3 times 10. The multiplication comes from how many times I add the 10. And it's basically a count of how many 10s I have. We know that this expression, by the way, has a value of 30. So we can check when we change the way the expression looks, right? This was just a rewriting of the same expression, and I maintained its value. 3 10s is 30. 10 plus 10 plus 10 is 30. So when I am rewriting some of these or simplifying, or sometimes it's called evaluating, right? I am trying to make the same expression that's not on a scale. There is no equal sign here. There's no solving I can do. There's only changing the way it looks without changing its value. So I changed 10 plus 10 plus 10 to be 3 times 10, and now that's 30, right? Over here now, so if I have multiplication, it means repeated addition. Now I have 10 groups of 10, but then 10 groups of those as well. So if I tried to write this out in addition, it would be a huge mess. It would be so many, right? But I can do it one piece at a time. And I could say that this is 10 times 10, or 100. And then this times 10 continues to be here. Now I have 10 100s all added up, and so that becomes 1,000. But there's another way to write that other than evaluating this, which is to find that it is worth 1,000. I could rewrite it using exponents, because repeated multiplication is an exponent. So this is 10 to the 3 power. It's how many 10s are all multiplied together. And that's what that means. Now 10 to the 3 power is still 1,000. I changed the way it looked without changing its value. Okay, so whenever we have an expression just floating in space that's not on a scale with variables that we want to solve for, we are trying to just maintain its value, and we can only do substitutions of equivalent expressions. 10 to the third means the same thing and has the same value as 10 times 10 times 10. That's the meaning of exponents. So if I come over here and I use the meaning of exponents, I can see that this squared here means I'm going to take 10 to the third times 10 to the third. Okay? Well, this is 10 times 10 times 10, and I'm multiplying that by 10 times 10 times 10. So 10 times 10 times 10 times 10 times 10 times 10. The meaning of exponents shows me that this is 6 total 10s, which before we took this repeated multiplication and turned it into an exponent. So the value of this is 10 to the 6th. Well, I could also see that that means I'm going to be adding my exponents, or multiplying them here, adding them here. So this is also 10 to the 3 plus 3, because it's 3 of them plus 3 more in the exponent. I am multiplying all of these numbers, but when I add exponents, it means I'm going to continue to multiply more of the same base. so that I could write it out like this. So this becomes 10 to the 3 plus 3, also equal to 10 to the 6. This becomes 10 to the 3 times 2. So I have raised 10 to the third to the second power, which has a meaning of 2 of those multiplied. So I can multiply these exponents. And again, it has the same value of 10 to the 6th. And then 10 to the 6th has the value of 1, 2, 3, 4, 5, 6, because that's how tens work. They just bump over the 1 in our base 10 decimal system. So it's always got a value of 1,000,000. It's just different ways to write that expression. And I'm using equal signs here not to say I'm in a relationship I'm trying to solve. There's no variables. I'm saying that these expressions are equivalent. I'm doing the same thing by showing this vertical shift, that these values are equivalent. These expressions mean the same thing. So if I wanted to do this, I have multiple options for how to do that. I could use the exponent rules to say this will be 10 times 10 times 10, whatever's in the parentheses, times itself, so that there's 2 of them, right? And then I can see that that is 10 to the 6th again. So this is yet another expression that means the same thing. I could have alternatively said 10 times 10 times 10 is 10 cubed, and I'm going to square it, right? But I want to show you one other thing. As I took my addition and brought it together as multiplication, I want to show that this multiplication that is repeated addition does in fact distribute across addition. So the value of this, if I do PEMDAS, would be 10 times 10, which is 100, okay? This expression has a value of 100. PEMDAS says do this and then multiply outside. But I could also list this as 6 times 10 plus 4 times 10, right? I could see the 6 plus 4 as, I could see the 6 plus 4 as a length and then multiply that by another length, my 10. And by doing them individually, 6 times 10 is 60, 4 times 10 is 40, I can see that the area they create through this single multiplication is 60 plus 40, or 100. I have not changed the value, but multiplication does in fact distribute across addition. When I add these 2 lengths, one of them is 6 long, one of them is 4 long, and I want to multiply by 10, I can do that individually, or with the rainbows if you want to see it. So this distributive property is still valid for multiplication across addition because of this relationship. Now I'm going to jump over here and say, well, repeated multiplication is exponents. I can change multiplication into a series of exponents. So I should be able to distribute that exponent across multiplication. Yes, I can, right? So instead of thinking of it as the meaning of the exponent is this and this, I could alternatively and validly say that this is 10 squared times 10 squared times 10 squared. Okay, I'm going to erase this for room. 10 squared times 10 squared times 10 squared is 10 times 10 times 10 times 10 times 10 times 10, right? So that is 6 tenths, still 10 to the 6th, still 10 to the 6th, still 1,000,000, right? I could also see this as 10 to the 2 plus 2 plus 2, because they're all the same base. But what I really want to show you here is this idea that exponents distribute across multiplication the same way that multiplication distributes across addition, because these are one step apart. Repeated addition is multiplication. Repeated multiplication is exponents. But this double jump does not work. this double jump, I cannot distribute this 2 across this addition or subtraction, okay? Because this is 10 plus 10 times 10 plus 10. Fundamentally different, right? This, or in PEMDAS, I could say that this is 20 squared. 20 times 20 is 400. So the value of this expression using PEMDAS, do what's in the parentheses, then do the exponents, right? Would be 20 squared. 20 times 20 is 40. 400. So I could also do it this way and say it is 10 plus 10 times 10 plus 10 using the meaning of exponents, and I get 100, 100, 100, and 100, or 400 total area when I square 10 plus 10. Now, what if I had done it wrong? If I had distributed this exponent, everything in red is wrong. This would be 10 squared plus 10 squared. Well, that's 100 plus 100, which is only 200. I'm leaving these other boxes out of the picture. I do not get the appropriate value. 200 is not correct, so I cannot distribute exponents across addition because they're 2 steps away from each other. So, this, let's go, this is good stuff, okay? This is okay. This is how it works. Oh, that turned it red. I don't like that at all. This is bad. And this is good stuff. Okay? So it's not that distributing is bad in and of itself. It's that these 2 are related in this way. And these 2 are related in this way. But I cannot jump a level. This will not work. So when you have addition mixed with exponents, please, please don't distribute. That's not a possibility. But do distribute exponents across multiplication, and do distribute multiplication across addition, whether these are numbers or x's, right? The reason we have these rules is so that when we change one of these to an x, okay, I'm gonna get rid of that. Go away. When we change one of these to an x, this is some math that we can do. Gosh, why is it not erasing? X times 10, and so this is now 10x plus 40. And it no longer has a value. I can't evaluate until I know what x is. But this expression is equal to that expression. This would be standard form. This would be factoring out the GCF. So we can go back and forth in this way, and that's a really fundamentally important algebra skill. So the reason we have all these different ways of writing expressions is so that when we introduce variables, we can treat them like just unknown numbers. That's what they are. They are our unknowns. And we can rewrite things in ways that will make it easier. Remember our lab where we had the volume of concrete, and it was this long drawn out product of x plus things minus other products, and then it's simplified to a simple trinomial. So just keep that in mind, that that sort of thing happens, and we need to be able to do that. Apologies again.